All right, I think we're live again. Hi, everyone, and welcome back to Astro Chats. As always, I'm your host, Erica Wright, Youth Astronaut Community Coordinator, and we're excited to have you here with us today. Before we get started, just want to remind everyone out there that you can join in on our conversation today through Twitter and Facebook using the hashtag Astro Chat. I'll be monitoring that throughout our conversation and presentation today. So go ahead and type them in there and I'll be asking our presenter as many questions as I can, and hopefully we'll get to most of them. So today we're in for a really exciting topic. We're going to be talking about how we observe the invisible. And I don't know about you, but that brings me a lot of questions. So hopefully we'll get some of those answered today. So to talk about this and dark matter, we have with us today Claire Lamman. Hi, Claire.
Hello.
Thanks for joining us. So before we dive too deep into what you brought to share with us today, I thought we might start out with a quick question. Over the past week or so, we've been talking a bit about careers, and I happen to know that you're working on getting your PhD right now. Could you tell us a little bit about what that means? I think a lot of our students and viewers might not know exactly what getting a PhD really entails.
Sure. Honestly, I didn't either until like several years after I finished high school. So I wish someone would have told me this. Right, so I finished middle school, high school. I went to college where I did my undergraduate degree, which took about 4 years. I did that in astronomy and physics. And then I applied for extra school, which is the PhD program. It's not as scary as it might sound. There's a lot less classes and more focus on doing research and teaching people. So I enjoyed a lot more than the other college I've done. So I'll be doing this for another 4 or 6 years until I get my doctorate.
Okay, great. Yeah, I think a lot of people don't realize that part of getting your PhD also means teaching some.
Yeah.
Yeah.
Have you practice right now?
Perfect, exactly. We're glad we could be part of your learning experience. So today, I think you've brought with us some stuff to learn a little bit about dark matter, which is really exciting and one of those topics I think
dark energy, yeah.
Sorry, dark energy. They are different. I am so sorry. Even better. So let's get started, I guess.
All right. This all looks good?
Give it 1 second. Perfect. Now we can see.
All right. So my name is Claire Lamman. I'm going to talk about dark energy. And I thought I'd start with just a really quick introduction to myself. I grew up and spent most of my life in Colorado. That's where I did my undergrad degree, my first part of college. And now I'm in my first year of the graduate program. So I'm still learning a lot about what it means to be a professional scientist. But so far, I've really enjoyed all the experiences I've gotten to have. I've been able to travel all over the world, go to really cool telescopes. This is a picture of me on top of a volcano in Hawaii. I've got to work with incredible people. And I'm learning about how to answer some really big questions that I've wondered for most of my life. Questions like, how did the universe begin? Does it go on forever? If it has an edge, what is an edge to the universe like? What will happen to it in the future? And what's up with dark energy? It took, for the longest time, I had no idea what it was, but it sounded really important. Now, astronomers know the answer to some of these questions already, others we're still working on. And almost all these questions have to deal with how the universe changes over time, which is a bit of a tricky thing to understand or to see, because the universe is changing all the time, but it does so really slowly compared to our tiny human lifetimes. So we can't just look up in the sky and watch the universe evolve. Instead, astronomers use sort of a unique trick to look back into the past. And it's all thanks to the fact that light takes time to travel, which is really weird because you don't notice it on Earth. All the distances here are really short. When you turn on a light, the room seems to light up instantaneously. But for things further away, like if we're looking at a star, it takes time for light from the star or the sun to reach Earth. I've had a lot of time in quarantine to come up with like cheesy PowerPoint animations. So this is special because it means that the further away an object is, the more time it's spent traveling through space to reach us. So we're actually looking at older light when we look at things that are really far away. And the further away we look in space, the further we look back in time, which is very useful. So if we want a good idea of what the universe looks like now and what it looks like in the past, what we need is a map. We have to figure out where all the galaxies are in the sky and how far away they are from us. Now, before I talk to you about how I'm helping to make a map of the universe, I want to quickly go over the current map we have for the universe. So I'm going to use a software called Worldwide Telescope, which is fantastic and something that all of you can access if you have a browser. I'll give details for that a little bit later. It runs rather slowly when I'm using Zoom. So for part of this, I'm just going to use a pre-recorded tour. It might take a little bit for this video to load. But
and while we're waiting, I'll actually.
Oh, here it goes.
Can we pause it for half a second? So while we're waiting, I'll actually plug one of our previous Astro Chats. Last Friday, we had Dr. Pat with the Worldwide Telescope Ambassadors take us on a full tour of the universe and gave us a little peek in how to use Worldwide Telescope. So this is great that we get to go on another specialized tour of the universe.
Okay, so you've already seen this. This will be quick. Hopefully I'll point out some things you might not have noticed in a first tour.
I'm sure
so you should be familiar with, you should be familiar with this. Here's the solar system, the sun, the planets. And down here on the right, I want you to notice Orion. Even though we're far away, you can see the 3 stars that make up Orion's belt. Now, although it looks like these 3 stars are close in the night sky, as we get further and further away from Earth, they start to shift positions because in reality, these 3 stars are all different distances away from Earth. So we're getting farther and farther away now. Notice how the stars shift. The poor Orion is melting. And now you see that the stars we see in our seemingly flat sky have a 3-dimensional distribution. As we go out even further, the Milky Way turns into the plane of our galaxy, the massive swirling disk of gas, dust, and stars that we live in. The center is so bright because it's filled with many stars whizzing around a central supermassive black hole. And now as we get out further, you'll see some of the neighboring galaxies. Andromeda's popping up here. And in the background, it's really faint, but you may be able to see bands of dots. These are swatches on the sky that we observed from Earth. But just like the 3 stars in Orion's belt, we were able to figure out how far away all the galaxies in these swatches were. So because we know how far away they are, we can create a 3D map. And so as we get even further, it'll start to take form. You guys got to see the Sloan data before?
Look at the Sloan data. I don't know that we looked at the Sloan data.
Okay, so this is real data. It was taken by the Sloan telescope, which is really similar to what I'm doing now. I want you to remind you that every dot you see right now is not a star. It's not a planet. It's an entire galaxy. Each dot is filled with hundreds of billions of stars and hundreds of billions of galaxies. And so we have what is quite literally the biggest map ever made. Now, to show you a bit more about how this is a 3D map, I'm going to try and show you it in 3D. So worldwidetelescope.org, you should know about it. So I'm going to stop sharing and then reshare my other screen. This is the same thing we were looking at before, but now it's I guess a live view. I'll control it. Here is a bunch of galaxies. And because this is real data, there's some weird things about it. So if I rotate, oh, it's very slow. So you can rotate a little bit. You can see that it sort of makes a butterfly shape. No, our universe is not shaped like a butterfly. That's an observational effect. So it looks like there might be these mysterious voids of the universe right here and here. Those are actually there because it's just hard to see galaxies there. When we look up at the night sky from Earth, the Milky Way is beautiful, but it's also filled with lots of gas and dust that gets in the way of seeing things beyond it. So there are galaxies in these gaps, we just can't see them because of all the stuff in our own galaxy. You also might notice that there's more data up here than down there. That's because these galaxies are in the part of the sky that the northern hemisphere can see, and these ones are in the part of the sky that the southern hemisphere sees. So Australians are a bunch of slackers. Now there's just not quite as many telescopes down there. And because this is going a bit slowly, I'm going to shift back over to my PowerPoint because I figured that might happen. So I have a flat picture of what we were just looking at. So this is the same data, but it's flat now, unfortunately. Earth is at the center. And as you look out in all directions, you're looking really far away. And because light takes time to travel, you're looking far into the past. And so you can see this butterfly shape again. The main thing I want you to notice about this is that there are patterns. There's a structure. The universe isn't just some big empty space where galaxies are randomly strewn about, but there are voids, places without a lot of galaxies, strands, clusters where galaxies are all packed really closely together. They didn't get the social distancing memo. And so this structure of the universe is what I'm helping to try to figure out, because it's different when you look at the structure close to Earth and when you look far away. And that's because the structure far away sends us light that's older. So we're seeing the structure at an earlier point of the universe. So what does all of this have to do with dark energy? Well, about 100 years ago, astronomers noticed that galaxies are moving away from us. And not just that, but the further away a galaxy is, the faster it was moving, which was quite a surprise to a lot of people. What it told us was that the universe was getting bigger everywhere, all at once. Now, if you run that backwards, you can see at one point everything used to be smaller in one really hot, dense place, which then quickly expanded, what we call the Big Bang. Now, people accepted this for quite a long time, and then only about 20 years later, or 1999, astronomers looked more closely at the motions of galaxies and found that not only is the universe expanding, but it's getting bigger faster and faster, which is really weird when you think about it. So here's a picture of the universe over time. It starts out with the Big Bang, it grows, but if you have an explosion, it goes off, everything gets bigger, you would think that over time it would start to slow down, especially because gravity likes to pull stuff together. But it's not doing that. It's getting bigger and bigger, faster and faster. So there has to be some sort of anti-gravity that's pushing everything apart, some weird form of energy that we don't really understand. We call this dark energy. And the amount of dark energy you need to explain this motion of the universe is a lot. This is a pretty popular chart, so some of you may have seen some version of this before, but it's quite striking. So only about 5% of the universe is made out of atoms, the stuff that you, me, viruses are made out of. Dark matter is about 25%, and then dark energy is 70%. Was there a question?
Oh, just checking.
Okay.
Not yet, and I have a question, but you might be getting to this, so I'm going to ask it and feel free to ignore it right now.
Okay.
Are we going to talk a little bit about the difference between dark matter?
Oh, that was literally the next thing I was going to say.
Perfect, because
yeah,
I don't know that I know the difference fully.
So they get confused quite a lot. But really the only thing, as far as astronomers can tell, dark energy and dark matter don't really have anything in common. They both have dark in their title because they're things that we don't really understand. So dark matter we've noticed because galaxies don't move how we would expect. And in order to account for how they move, we say there's probably some extra matter there we just can't see. Dark energy is that the universe is moving in a way we don't expect. So we think there's an extra type, some weird force that's doing stuff to explain a motion we don't understand. So there's, I would say, even more we don't understand about dark energy than dark matter, because we have a lot of questions. We don't know what it is. We don't know what it's like. Like if you could somehow get a box of dark energy, put it in a lab and poke at it, what would happen? And some people wonder if it even exists at all. Maybe we just don't understand gravity enough. Maybe on really large scales, it actually would make sense for a universe to get bigger faster and faster. Something about dark gravity you can only notice there that you don't notice on Earth. Now, there are many different models of dark energy, and using these models, astronomers can create simulations that would predict what the universe would look like with these different versions of dark energy. We have lots of models, but what we need now is more data. We need a better map so we can distinguish between different ideas for what dark energy is. So, how do you go about creating a big map of the universe? So, I'm just going to do this rather quickly, but it is, I think, pretty cool. To map out the universe, you look at galaxies and you look at their light. You can break up their light into the different component parts of the light, and you get a rainbow. Just like if you have a white light that passes through a prism, we're looking at galaxy rainbows. Now, this spectra of light will change based on how galaxies move. It happens for anything that's moving away from you. If a galaxy is emitting light and it's moving away from us, as it moves away from us, its light is stretched out, and so it looks more red. So the redder a galaxy looks, the faster it's moving away from us. And because of what we know about how the universe expands, we know that the faster something's moving away from us, the further away it is. So it gives us this really, really nice relationship. Basically, the redder a galaxy is, the further away it is. It is beautiful, and what we use to figure out how everything is mapped out in 3D. So we need spectra of many galaxies. This is going to be done by DESI. This is the collaboration I'm part of. It's called the Dark Energy Spectroscopic Instrument, and it's located inside this telescope you see right here on Kitt Peak in Arizona. And inside that telescope, there's this crazy complicated instrument that I certainly don't understand all of it, but it is quite ingenious. So we want to observe millions of galaxies. That's a lot. They had to come up with a way to look at lots of galaxies at the same time. So inside this instrument, there is a plate. You can see this right here. It has lots of dots on those. There are about 5,000 of those dots, and each one is a tiny little robot. The idea is that each robot will point at a galaxy. It will gather light from that galaxy. And you can see an actual picture down here. When it gets light from that galaxy, it will transfer that information down to spectrographs. So it transfers the information with fiber optic cables. So if you've ever played with a toy like this, this is how it passes that information. And then the spectrographs down here will break up the light, figure out the redshift of each galaxy. Now, although these robots move by themselves, we still have to come up with an algorithm to tell them which galaxies, how to decide which galaxies to look at, which is an important problem because you want to make sure that you're observing as much as possible, you're getting the best data possible, and helping work on that algorithm, which decides how to communicate with the tiny robots, is what I have been working on for most of this year. Now, I also want to say that this collaboration is huge. It's a lot more than just me and my advisor working on stuff. There are hundreds of people all over the world that are part of this, which is cool. I love working with the data. I like helping to answer these questions, but it's also exciting to work with people from Mexico to Spain, Korea, and we have meetings about twice a year. We get to go to really exciting places like Madrid and Cancun and Ohio. So I love working with these people. They're all so different. They're all so smart. And it's just really been a great experience. Now, this survey is actually scheduled to start like any month now. Unfortunately, the mountaintop was shut down thanks to COVID, but hopefully, I think this year it will be able to get started. We've already been able to get some data, so I'm really excited to see what it will figure out. So I'm just going to go through, I just covered a lot. I'm going to go through that, summarize it really quickly, kind of in reverse. So we're going to have 5,000 tiny robots that will look at the sky every night. Each one will look at the light from a distant galaxy. They will see how red that light is. And remember, we will see how red the light is and remember that the redder it is, the further away the galaxy is. We can use this information to create a 3D map, and we can look at how the structure changes when we're looking at galaxies close to us and when we're looking at galaxies far away, where those far away galaxies are sending us older light. And then with this information, we can hopefully figure out some great things about dark energy. So I want to end by saying just a quick little thing about myself. And that is that even though I'm a scientist, I have always thought of myself more of a creative person. I still do. And so I don't spend all my time just sitting at computers doing math. I really try to do fun projects. So for instance, I made a cake that is the cake version of the telescope we used to observe on, and also a cheesecake that has raspberry sauce to make the 3D map of the galaxies you saw.
Those are beautiful.
Thanks.
I'm a cake maker myself, and those are gorgeous.
Thank you. So I didn't really think of myself as a math or a science person, which was worrisome for me because when I was, I wanted to be an astronomer for a long time, but I didn't think I was smart enough. So I recently found a journal entry that I made when I was in 6th grade. So I don't know, I think that's maybe a little younger than some of you are now. But the only thing worse than my handwriting was my spelling. But I said that I didn't think I was good enough at math to be an astronaut. So now I'm going to be an astronomer, which is a bit funny because astronomers generally use more math than astronauts. But I was concerned. I was thinking, how could I be an astrophysicist if I'm struggling with algebra? But what I wish I would have known is that when you start to learn more advanced math, it's not like it gets crazy more difficult, because I'm building on information I already learned. And so I wish I would have stopped worrying about if I was good enough at math, because what I found is that being persistent and finding creative ways to solve problems is a lot more important. So basically what I'm trying to say is that what I've learned is that you don't need to be a genius to help answer some of the biggest questions about the universe.
Thank you. Thank you so much for that, Claire. That was fantastic. And one of my favorite points of that I've been asking a lot of our guests is kind of this idea of, have you always wanted to do this? And if you did, have you always felt like you were prepared to be able to do your work that you're doing now? So it's great to hear and kind of help relieve some of that stress from our young audience, that if you're not, an A++ student in math today, that's okay. Are you continuing to work at that? And that, as long as you continue to try and ask for help, that you can get to a point where you're confident in your math skills to be able to do the work that you're doing.
Absolutely.
So thank you for sharing that on your own. I didn't even have to ask. That's fantastic. So Claire and I are going to start to ask some questions here. If those of you out there watching want to join in the conversation, please feel free to ask them on Facebook and Twitter using the hashtag Astro Chat. I'm monitoring that as we talk, so if I look away, that's what I'm doing. But please ask away, and as we wait for some of your questions, I might ask a few of my own. Let me just refresh this to make sure I haven't missed any questions here before I do that. Gotta keep track of all the different feeds. So you talked about struggling a bit in math in middle school mostly, right? Were there any of the classes that you either struggled with or ones that you loved that maybe you see now as being beneficial to you that maybe people wouldn't expect?
This isn't really related to astronomy, but I hated history class, and now I found myself thinking more about history class than I do what I learned in history class than other classes. Writing was one that I always really liked English. I love writing stories, writing essays. And that is huge in astronomy because especially when you're working on something like this, you don't get money unless you convince people that what you're studying is interesting. And so if you can't write well, it's really hard to be an astronomer. So that skill, I think, has helped me so much more than any math skills. I can write well, and it's helped me get into colleges, get grants. And that's something I didn't really think about when I was younger.
I think that's a really great point. I think a lot of young people that are interested in science, and it's not just astronomy, it's all of the sciences and STEM, technology, engineering, and math fields, is they think, oh, I don't need math. I mean, I don't need writing. I'm good at math and I'm good at physics. I don't need writing. And to do research, especially, but even other fields that use these sciences still require a good foundational ability to write. And I think it's maybe different than creative writing, although there are definitely some parallels to those two. I think it's really important to remind people that in many of these jobs, you have to write not only to get the money, but then once you discover something, perhaps you come up with something, you have to share that with the scientific community. And a big way to do that is writing papers. So
yeah, and that's where creativity, even like creative writing, can play a big part too. I've seen so many really cool science results that are able to get spread out to a lot of people because the scientists have come up with a cool way to share it. And they've wrote poems, videos, or come up with creative presentations. So I've been able to use creativity, yeah, quite a lot more than I thought.
great. So you mentioned a little bit about your college career. Could you tell us just a little bit about more kind of what classes you took, how you chose your major? Obviously, you knew you wanted to be an astronomer, but
Yeah.
just a little bit more about that.
Yeah. So my goal was always being an astronomer. Astronomer would be like the top goal. So I'm gonna start with that as my major. And if it's too hard, then I'll figure something else out. But I might as well start with the hard choice. My goal was to never have to retake a class. I said I'm never gonna fail. And I ended up actually doing really well. Like I got really good grades. It was not as scary as I thought it would be. In fact, I declared a second major in physics. So I doubted myself a lot more than I needed to. But I took physics classes, a lot of math classes, astronomy classes, of course, were the best. And one thing I cannot emphasize enough is programming classes. If you are interested in astronomy or any science field, learn programming. If you don't know it by the time you get to college, try to take a programming class as soon as you can. My fiance is a computer science engineer, and I always joke that it would be easier for him to find an astronomy job than me, just because he knows programming. It is so important.
I think that's a great point. We've talked about this a few times over the past week as well, that the writing skills are important, but the programming skills are important because as astronomy relies more and more on more data, right? You're talking about how we need much more data, that being able to program and start looking at that data, not by hand, but using different algorithms to kind of sift through that is really valuable, and kind of invaluable because it's just too much data to look at.
Yeah.
So I think that's a really great point to bring back up. Thank you. Let's see. Let's check here for a second. You were so good at your presentation that you actually answered a lot of the questions that I normally would be asking, so, which is, I appreciate that. Oh, go ahead.
Yeah, I was saying during my undergraduate college, I worked at a planetarium doing planetarium shows. This is my first time giving a presentation since leaving there, so it was really fun to do. And I guess another example of how I've found a way to use creativity in this.
Great. Yeah, well, we're really happy to have you here. And again, that was a fantastic presentation. I feel like I learned a lot. Actually, though, I think we'll go back a little bit to some of the science content because that's why a lot of our viewers are here. I'd like to back and forth between the science and then the career aspects. So we're actually tomorrow going to dive even more into telescopes as time machines, so that looking back in time with our guest tomorrow. So that was a great primer for tomorrow's talk. But we started touching a little bit about how we're going to start to understand slightly better dark energy. And I think one thing that's really valuable here is the types of questions that don't have answers right now, right? That there's still a lot of questions around dark energy, that science is unknown. Like that's the whole point of science. We talked a lot yesterday about uh, most of our middle school viewers are learning science that someone else has already discovered. Um, and that's okay. That's how we build our foundation. But now we're starting to ask some of these questions. The farther you get into your science career, you get to start asking questions that no one's looked at. Although that's not to say you can't start asking those questions now, even as a middle schooler.
Right.
So what were some of the first questions that you started exploring, that you didn't think anybody else had an answer to? Did you get to do any research in undergrad? Did you get to start asking some of those questions?
Yeah, that was actually what you're saying was actually frustrating for me when I first started research because I felt like I wasn't doing anything new. I felt like I was slowing people down. I was just learning things. What I didn't realize is like that's the point of early research. It's not necessarily for you to solve the universe, but for you to learn how to do that in the future. So as my undergrad, I had a really cool experience where I got to go to Hawaii for a summer. That was where that picture was from, and go through lots of data of M dwarfs, which are really small red stars. And I found a way to go through and look at a lot of them very quickly when I was there for the summer. And I developed a tool to analyze the data, and I didn't really get to reap any of the rewards of seeing what science we could learn from it. So my main project in undergrad was then looking through that data and trying to come up with trends that we can use to understand how little stars form, which is something we don't know actually a lot about. They're a lot harder to observe because they're small and faint.
Yeah, great. That's a really great experience and a great example of how the process of learning how to do the science is just as valuable as doing the new science. And maybe you get to find a little something too along the way.
Yeah.
So another thing I'm kind of interested in is at the beginning you mentioned a lot of those big questions about the universe, right?
Right.
How do we know it's getting bigger? All of these deep questions, and you seems like right now you've kind of settled on dark energy as the question you're most interested in. How did you decide that that was the thing you wanted to explore more?
It's the biggest open question I think that there is left. So I didn't really answer those other questions, but does the universe go on forever? Yes, it looks like the universe is infinite. The universe we can observe doesn't go on forever though, because light takes time to travel. The universe has only been around for about 14 billion years. So we can only see things 14 billion light years away. Basically, there is stuff all around us, but most of it just hasn't been around for long enough for its light to reach us. So the answer is that yes, the universe is infinite, but practically there is kind of a boundary. What will happen in the future? So dark energy is ripping the universe apart faster and faster. We're not sure exactly what will happen, but with the models we have now, it looks like everything at one point will get ripped apart. So galaxies are moving away from us. Eventually, we won't be able to see any other galaxies except for the ones really close to us, like Andromeda. And then if the universe keeps going in that direction, we'll just live in a really, really empty, sad universe. But that will be like billions of years from now, so you don't need to worry about it yet.
And I think that's one thing we always have to remind ourselves is a lot of these big, scary sounding things in astronomy are so far in the future that it's nothing we have to worry about, but they are things that we are interested in helping us to better understand the world around us and the universe around us.
Yeah, and I think we're actually lucky. Humans live at a really cool point in the universe. We are living at a time when the universe is old enough so that we can actually look back and see how the universe has changed, how the structure we see has developed. But we aren't living in a universe that's so old that everything has already moved so far away that we can't see it anymore. So we're kind of lucky in that sense.
Yeah, I hadn't thought about that, but that is a really good point. That's a lucky place in space and time. So want to dive a little more into dark energy just because I think there's a lot of questions out there, but I'll be honest, I don't even know what those questions are yet because
Yeah.
it's such a new, i- interesting, hard topic to understand. Are there any questions that you've heard people ask that you found really exciting about dark energy?
Yeah, just trying to understand what we do know about it and how we try to model it. So, dark energy is, I almost want to say, a placeholder to try to explain why the universe is getting bigger, that something is beating gravity. Dark energy is kind of like an anti-gravity term, but we can figure out some of its properties by modeling the universe as kind of like a fluid. So we can see, oh, it has these different forces which cause it to do this. Um, and in order to explain what we see now, there has to be this extra energy term, assuming that we understand gravity well. So that's one of the more specific things we're trying to figure out about dark energy are some of the numbers associated with what we call its equation of state, basically how it behaves, how its pressure and density relate to each other. So we're kind of treating dark energy as a thing, a physical thing, but it has properties that we can try to learn about. What we've learned so far is that it has negative pressure, which is super weird.
That does sound really weird. I don't know how.
Yeah, so it's the idea is that like normally if you have, I don't know, say if you have a ball and you try to squeeze it, the ball will resist. It'll like push back. But dark energy is the opposite. So one way I've heard it described is a piston. So if you have like, I don't know, a syringe or something and you're pulling it out, but it still wants to pull back. So
Okay.
it's dark energy, and that's how I've heard it described as dark energy having negative pressure. It's sort of, honestly, it's sort of a rough analogy, but it's
No,
weird.
that gives a good sense of the kind of pressure or energy that we're talking about, right? That kind of
Yeah,
pulling something away in that pistony kind of way, or if you had a plugged syringe might be something
right.
that somebody else could visualize if our guests don't know what a piston is, because
Yeah, I think another good way to describe it is that it's almost like it's sometimes called the like vacuum energy density, and it's almost like there is an outside to the universe, which doesn't make a lot of sense, right? Because the
no.
universe goes on. But let's say there's an outside to the universe. It's almost like there's some sort of vacuum outside of it that's pulling things towards it, just like the vacuum of space.
Right. So that's kind of what we're seeing happen, but we don't know what's causing that, right? We don't assume there is
Yeah,
a vacuum outside of it. That's the end
that's what it
result.
feels like.
That's what it
Yeah.
feels like. Okay. Yeah, that gives me a better sense a little bit of what's going on. Um it's this is why it's one of the most exciting topics, right? It's just so confusing. Um, right? There's just so much
And
we don't understand. And I think that's a really great point to keep emphasizing is that there's some of these really big questions that we still don't understand. So you talked a little bit about how the group that you're working with is building a map to better understand dark energy. Do you know about any other types of research that are happening out there to kind of come at dark energy from other perspectives, just to better understand?
yeah. So the main two ways to start to study dark energy, which I kind of talked about, are creating observations and then creating simulations. Because the observations won't really tell you anything unless you have predictions, which is all about what science is. So the DESI collaboration actually also has theorists in it. I would call myself an observational cosmologist in that I look at data to understand the universe. But there's a lot of other people who use supercomputers to create really high resolution simulations of how the universe would evolve and what the structure would look like at different points if maybe say dark energy was a bit different. And that's really invaluable when we're using the data.
Okay. All right. So there's kind of these two prongs to
Yeah.
understanding it that
So there are astronomers in my group, like we tease them that they don't like telescopes. They don't want to go to them. They just like working with their supercomputers. And that's okay. Astronomy needs all sorts of scientists.
great. Yeah, I think that's a really great point that there's lots of different types of people needed and different types of research needed to be done and instruments to do it. Um, so I think another question I have that's a little not quite as dark energy related, but more about you and perhaps our audience out there is uh, what advice would you give someone who's interested in entering maybe not just astronomy, but science, some sort of science career? What kind of advice would you give them if they're kind of thinking about that as a trajectory?
Right. I would talk to people, learn about, find, think of the questions that you're interested in asking, and then see what the scientists who answer them do day to day. So I think like the fact that you guys are listening to chats like these is perfect. Maybe you're really interested in some like a biology question, but like you really don't like, you don't think you'd be happy doing the work every day that they do. So think about that when you're like looking about the different fields. And then if you find an area you want to go into, or just you decide you want to go into science in general, don't be discouraged by math. Keep trying if it's something you struggle with, and learn how to program. That's the biggest concrete advice I can't repeat enough.
I think that is, I think if our audience doesn't pick that up from all of our different visitors, I think I will be shocked.
Yeah.
And I think it's really important. Yeah, like you said, it's important beyond just astronomy. It's important throughout the science careers and even beyond science careers. Programming is becoming more and more critical. You made out a really good point of asking people what they do day to day, and you've talked about pieces of your day to
Oh,
day.
right.
Could you describe kind of a typical day for you right now as a PhD student researching dark energy and working on your own degree?
Right. Since I'm an early PhD student, I still have to take classes. So a good chunk of my time is taken up by sitting in classes, working on homework. I found the homework is a lot better than other homework I've had. It asks like there's less problems, but they're harder. So you just kind of have to sit and think about them more, which I like. And then the research side of things, a typical day, I might spend hours trying to figure out why I'm getting an error in my code. I might sit sometimes with a scratch piece of paper and try to think about how I can structure my code to solve a problem more efficiently. That's where creativity comes in. I might just be quickly writing really quick bits of code to create quick plots, just so I can get an idea of data that I'm working on. I talk with my advisor who's brilliant and gives lots of tips like, oh, you should look at this and this is probably where it goes wrong. And that's basically it. Like I spend most of my time programming, but it's more exciting than it might sound because every problem you deal with is slightly different. So I mean, maybe that's a good thing for some people, maybe it's not. But yeah, I can spend weeks programming things just to come up with like one plot, but that one plot is very rewarding.
Wow. I never thought about that, how long it might take to create a plot, but how much that plot might tell you something.
Yeah.
Towards one of your questions. I think that's a good point. I think typically when we're thinking about plots in middle school, it's something we can do in an afternoon, data that we're kind of starting to explore, but understanding the basics of how we maybe plot some of that data helps us to be better able to create the plots that you might be creating now, right? There's the basic plot, and then they can become much more complicated and deciphering the data. So,
Right.
I think that's a really great point. What?
Yeah, I was just saying with like plots, and as I've like done more and more, done sites at lots of different levels, a step up to the extra level has always just been, but you also have to consider this. And so that's basically what my science career has been, an ever increasing amount of, but you also have to think about this.
Interesting. So it's not that it shifts drastically, it's just that you add a little bit more as you go.
Right.
That's a really great way of thinking about it, is that everything you do builds on the past, and you just make those ideas a little bit more complicated and bringing in extra pieces of data, knowledge into that viewpoint. Great. So I also like to give you an opportunity, our guest speakers here, to share something else that maybe didn't make sense in your presentation, but that you would like our audience to know. Is there anything that you think is valuable, either scientific or career-wise, that you just feel like they might be interested in?
I'm not. not really sure.
That's okay. It's kind of it's a big open-ended question. But
Right.
sometimes as we're creating these presentations, we're like, we want to tell a story. I think that's a valuable part of sharing science is understanding the story we want to tell. And sometimes there's something that just doesn't fit in that story. So I like
Right.
to give that opportunity, but it's okay if that's not a thing too.
I, I guess one big thing about more my career that was kind of different than some of my peers. But when I went to grad school, I didn't know what I wanted to study. Like I knew I wanted to do astronomy, but that's a big field. So was I going to look at stars, galaxies, planets, cosmology? I had always wanted to do cosmology, but I actually, and when I say cosmology, I mean studying on really big scales how the universe changes and evolves, what I'm doing now. I never did that as an undergrad. I studied really small stars. So I was scared. I honestly, I still kind of am. I don't have a lot of experience in this field. I'm learning a lot very quickly. Um, and so I just want to say that, like, that's okay. It's all right if you know you generally want to study astronomy, but you don't have like this specific lifelong question you're going to answer. People change what they work on all the time.
I think that's another really good point. I think um, we feel like we have to know everything we want to do 20 years down the line. And that's not how it ends up being as we get farther into our careers. That, there's so much you don't know about astronomy when you're first interested in it. So, how would you know what you want to specialize in until you get a better understanding? So,
Right.
great. Thank you for sharing that point. Um, I think you kind of shared one exciting thing, but I like to also just give an opportunity uh, to showcase a little bit more about you outside of your science. So you shared with us that you bake very beautiful things.
Yeah.
Is there anything else you think our audience might be surprised to know about you as someone who's an astronomer, a cosmologist?
Yeah.
Something else about you that might surprise them?
I play a lot of music. Uh, I play a lot of different instruments, including the organ. So I'm part of the like Harvard Organ Society. I get to go. It's for me. It is just the perfect break because you use so much a very different part of your brain to play music than you do programming. And so if I'm stuck coding something, I could either spend a few hours being stuck, or I can go and play the piano for 10 minutes and then come back and figure it out right away. Like you might think I'm exaggerating, but I love playing music and it is so helpful.
Interesting. It kind of frees up your brain a little bit,
Yeah.
gets you stop focusing so then you can look at it from a new perspective. I think that's a really great way to think about it. And I know I really got to look into this because now you, I think, are our fourth or fifth guest, because I actually know one person didn't mention it, that plays music.
So many people play music. Like so many of my astronomy friends play music.
Yeah, I think that's really interesting. I'm sure there's some sociologist out there who's studying it, how high a concentration there is in musicians. So.
Maybe one of the viewers could survey a bunch of PhD students and see if astronomers are more likely to play music.
Right? That's a question out there. Wonder if there's a connection. So I think we're closing in on the hour. I've been so thankful to have you with us today for sharing your science and your research with us. Hopefully those of you out there that maybe if you didn't ask a question live might want to post a question on YouTube and maybe we can follow up. Yeah, not on YouTube. We can't post on YouTube. On Twitter or Facebook, and we'll follow up with those questions. So please do share those online with us and we'll get them answered as best we can. We have a few more people throughout the month who are going to talk about dark energy and dark matter. So if those questions, you just hadn't had it formed yet today, because I know, like I said, even for myself, these topics take some time to pull them in before you can figure out what the question is you want to ask. Go ahead and ask us online using the hashtag Astro Chat, and we'll get back to you either in a future session or online. So thank you again so much for joining us today, Claire. I had a wonderful time. I learned a lot. Like I've been telling everybody, I think I'm learning as much as our viewers as we go through. So I'm enjoying the experience. And thank you all out there for joining us for another session of Astro Chat. Hopefully you'll join us again tomorrow at, I forgot to write the time down for tomorrow. Tomorrow at 10 a.m. with Dr. Charlotte Mason, who's actually going to tell us a little bit more about that telescopes as time machine, how we use them to look back in time. And she actually studies those really small, distant, I should say distant, small on our visual observations, red-shifted galaxies. So she's going to dive a little bit more into that. So I think it's a perfect follow along today. So if you enjoyed learning about what Claire had to say, hopefully you can join us again tomorrow. And thank you so much again for joining us today, Claire. This was a great experience.
Thanks. I had a lot of fun.
All right. See you all next time.